Okay, now we're going to try a two-tailed test. This time the two-tailed test is going to be in relation to alpha 5. Alpha 5 is the coefficient on half baths. And we are going to hypothesize in the null that alpha 5 is equal to 0. Okay? This is probably a case where our a priori belief is still in the alternative. That is to say, we probably think half baths should be in the model. If we truly thought that alpha 5 was equal to 0, we wouldn't really put it in the model anyway. So we're okay here. Just as an aside, anytime you have a two-tailed test, the equality must go in the null hypothesis. And that's because when we're sort of trying to figure out the critical values, we have to center that distribution on an actual number. And so the equality part that we want to center that on, in this case, is 0. Anyway, that's a bit of a technical footnote, not the main purpose of this exercise. So what we want to do is we want to set up the hypothesis test now. In order to test this hypothesis, we have to have a test statistic. That's number one. We're going to use the t statistic, t hat, and that's going to be our alpha 5 hat minus the value of alpha 5 under the null hypothesis. That's where this comes in. There's our alpha 5 HO, so that's going to be minus 0, divided by the estimated standard error of alpha 5. So if we look at this column right here, it's going to be the estimated standard error of alpha 5 that we're going to end up using to compute this. Okay? And that's actually going to equal 7108.46 divided by 10503.3, which it turns out is produced in the third column of our output and will be 0.68. Okay, so just a note that this t-statistic column that's produced by Excel or Stata is always the t-statistic for a hypothesis that's tested in relation to 0. So if we have anything other than a 0 here, we'll have something other than a 0 here, and these are then not the correct statistics to use. We have to calculate them by hand. But if the test is in relation to 0, we can actually pluck the t-statistic right from the table to conduct our test. So in this case, we know that it's 0.68, actually. Okay? Next thing we need to do is to find a critical value, right? Because our decision rule is going to be what in this case? Actually, I should talk about the decision rule first. We're going to reject HO if the absolute value of t hat is what? Well, greater than our t critical, associated with a certain number of degrees of freedom and a certain probability of a type 1 error. Okay, we could actually write that in the notation. We could put functional form notation and say this t critical is going to be a function of degrees of freedom, and it's also a function of the level of significance of the test, which in a somewhat confusing tradition is denoted alpha. Level of significance is just the probability of a type 1 error. Okay. So we pick those two things, and the t-table will kick out a t-critical for us. We have no reason to worry about the sign now, because we're really looking at a t-hat distribution centered on 0 under the null hypothesis, and our rejection regions are now divided in the upper end and lower end of the distribution. So if our t hat is sufficiently negative here or sufficiently positive here, we will reject the null hypothesis that it's equal to 0. Okay? So we don't have to add the second part of the decision rule, which says look at the sign. We don't really care about the sign anymore. So this is the decision rule right here. That's the one we're going to use. Okay? So what we need to do is look up the critical value, TC, in the table. We have still 11 observations. 1, 2, 3, 4, 5, 6, 7, 7 coefficients. So 11 minus 7 is 4. We have 4 degrees of freedom. This time we're going to follow a two-sided test. And let's go ahead and pick the 5% level. The researcher, we, get to choose that. So we're going to pick the 5% level for a two-sided test. That's this column. We're in this row. And therefore, there's our special number. There's t critical. In this case, the absolute value of the t statistic is 0.68. The t critical is 2.776. And therefore, we fail to reject. We fail to reject HO. Could we be committing a type 1 error in doing so? The answer is no. The only way you can commit a type 1 error is if you reject HO, and HO happens to be true. We failed to reject HO. So we could be committing a type 2 error by failing to reject HO if in fact HO is false. But we don't know that probability, and we don't know whether it's true or false. But this is what the evidence in our sample leads us to believe.